Welcome to module 33 of database management systems. This is on transactions again. This is the third and closing module on transactions, and we will discuss recoverability issues and some more of the serializability issues in this module. In the last module, we have talked at length about serializability, and specifically we looked at what is known as conflict serializability and the algorithm to detect that. Now, we would bring in another perspective, is if while a transaction is in execution, what if the system would fail? The failure may be due to hardware, software, various different reasons, power outage, disk crash and so on. So, when that happens, the database is likely to come into an inconsistent state. So, we would like to discuss how to recover from that inconsistent state and bring it back to a consistent state. We would also look at that going forward from conflict serializability, what are the other notions of serializability that can be used to serialize transactions, and we will look at a weaker definition of serializability known as view serializability, which can serialize more schedules than what conflict serializability can give us. So, these are the topics to discuss, and we start with recoverability and isolation. So, what we have done is we have seen the serializability help us if we think in terms of the acid properties that we started by defining as the desirable properties of the transactions. We have seen that the serializability significantly helps us to achieve isolation and consistency of a schedule. Yet, the atomicity and consistency may be compromised if there is a system failure. So, we had talked about this example a bit earlier. Again, let us take a look. So, this is a transaction where an amount of $50 is being transferred from account A to account B. So, we first read debit and then write on account A, and then read credit and write to account B, and we have added a seventh instruction, which is commit, and I will talk more about that in this module, which makes the changes to A and B permanent and shows the result to the user as well. Now, what happens if the system fails between step 3 and after step 3, when A has been written, and before step 6, when B has finally been written. So, naturally $50 will simply disappear, because what has been debited from A and will be available to be seen in account A will, the corresponding credit will not be visible. So, this leads to inconsistent state, and to handle that, what we need to do is to roll back the transaction, which means that we need to undo the changes that we have already done. So, we have to again go back to account A and write a new value, which was the earlier value, the value before the debit had happened. And this process of restoring the consistency back to the database is known as the recovery process. So, we say that so let us define a schedule to be recoverable if a transaction T j reads a data previously written by a transaction T I, then the commit operation of T I must appear before the commit operation of T j. If that happens, then that is the earlier transaction which has written the data, and T j, the later transaction which is reading that data, the earlier transaction has to commit, that is make the changes permanent in the database before T j actually reads it. If that happens, then we say that that schedule is a recoverable schedule. So, consider a following schedule of transactions T 8 and T 9, where T 8 has read and written A, but has not committed. That means some more tasks in T 8 are still pending, it has not finished, but T 9 then reads A, which is in terms of serializability it is fine, but then T 9 commits, and then T 8 is again trying to read B, it continues. So, what happens is what if the transaction will fail, the transaction T9 will fail immediately after the read operation. So, what will happen, I am sorry, if T8 aborts in between, then what will happen, that T9 would have read, because say in read B of T8, T8 aborts, that is it fails, then T9 has already read the intermediate value of A and has committed, which means it has possibly shown it to the user, but T8, since it has aborted, since it has failed, it has to be rolled back and the original value of A will be rolled back, which is different from what has already been shown to the user, and he will reach an inconsistent state. So, this is an example of a schedule which is not recoverable. Now, let us also observe that a single transaction failure not only means that one transaction needs to be rolled back, but it could have a cascading effect, that is, a series of transactions may require a rollback. So, here is an example of T10, T11 and T12. So, T10 reads A and B and writes A, and then T11 reads and writes A, and T12 reads A, and at that time if T10 fails, if that aborts, then naturally it is not enough to simply roll back T10, because if we roll back T10, then we the value of A goes back to the original, and T11 would have a wrong value which T10 had written, but has now been undone, has now been rolled back. So, it means that T11 will also have to be rolled back. Similarly, if that is rolled back, then naturally T12 also have to be rolled back, and so on. And when this rolling back goes from one transaction to the other, we say this is a cascading rollback, and this can lead to a significant amount of work. So, what we would prefer is if we could have schedules where such cascading rollback is not required. So, and there is a condition through which you can achieve that. So, if we have a pair of transaction T I and T j, so that T j reads a data item previously written by T I, then the commit operation of T I has to happen before the read operation of T j, which means that said in other words, that T j should only read values which are already committed and not read intermediate temporary values of other transactions. So, every cascadable schedule is also recoverable, because you can individually recover that, and it is desirable to restrict schedules to those which are cascadeless as far as possible. We will say that in not all cases that is possible, but if it is possible, we would like schedules which are cascadeless, so that our rollback work, the extra work can be minimized. So, here is an example which we had just seen, which is not a cascadable schedule. So, going forward, let us take a couple of examples of very similar transactions, and we would see when their schedules are irrecoverable, when their cascade dead recovery is possible, cascaded rollback is possible, and when cascadeless rollback is possible. So, here what I have done is I have shown here the two transactions T1 and T2, and this is what transaction T1 is doing, and we assume that in the database the initial value of A is 5000. So, this is what will happen. A is read here, and this value is a different A. This is in the buffer or the memory of T1 transaction, where A becomes 5000, then you subtract 1000, and then you write back. The moment you write back in the database, in between the value in the database is not changing, it is only that value is only in the buffer, and when you write back, the value in the database has changed. And then transaction T2 reads that value. So, in its local buffer, A becomes 4000, it increments by 500 and then writes it back, and when that happens, then in the database also the value has changed to 4500. And then T2 commits, and at this point let us assume that there was a failure. So, this is the point where there was a failure. There were other instructions in T1 as well, which is not of our interest right now, and then T1 would have committed. But what happens if the failure happens at this point? Naturally, the T1 needs to roll back, T1 needs to undo this and set this value 5000 back into the database, but that would mean that what T2 has committed, T2 has already committed this value 4500 in the database, and therefore, that has been probably been used in other places and shown to the user. That will create an inconsistency in the database. So, this is a schedule of T1 and T2 which cannot be recovered from. So, let us so what has been violated, that T2 has actually read a value which was in transit, and then it has already committed based on that read value. Now, let us look into the next. So, what has been done here, that all the changes are the same, but only point that we have done is we have changed the point where the commit happens. Again, still the T2 is reading the same value in A, and is making the updates 4500, but the commit happens at a later point of time after the commit of this transaction T1 has taken place. So, this is recoverable, but if we want to recover T1, naturally that means that for T1 to be recovered, I also need to recover T2, because T2 is used a value which is not going to be the value after the rollback of T1 has happened. T2 has used 4000, but after the rollback the value in the database will be back to 5000. So, it is the rollback is required for T1 as well as in T2. So, this is a case of cascading rollback that has happened. So, it's more work is being done, and that has happened because T2, now here the rollback is possible because T2 is committing after T1. So, the transaction it is reading from, it is actually committing the changes after that source transaction has committed. So, that satisfies the condition of recoverable schedule. So, you are able to recover, but it still required the cascading, because T1 had read a value in here of A which was not yet committed. So, if we would have committed that, then we would have been able to actually create a schedule which is cascadeless, as we will see in the next slide. So, now what the change that has happened is the commit is done right after writing the value of A, and T2 reads that only after that commit has happened. Earlier it was reading before that commit has happened. So, once T2 reads it after this commit, so if there is some requirement of if there is some situation of rollback, then only T1 needs to be rolled back, and T2 does not need to be rolled back, because it has used a value which is already committed. So, this is the basic through the example you can clearly see what is how the rollback can happen, and in a later module we will discuss the processes of how to do this kind of rollback, the cascading and non-cascading both kinds, and show how to go ahead with that. But now, for now what we learn is schedules need to be recoverable, and preferably cascadeless rollback recovery schedules are preferred in case of database transactions. Now, let us move on and talk little bit about what is available in SQL language in terms of handling transactions. So, SQL we have seen the kind of DDL, data definition and data manipulation language parts, and those were discussed in terms of our interactive session as well. As a part of data manipulation, it is also possible to specify certain specific transaction events. So, a transaction in SQL typically begins implicitly and it ends by a commit work, which says that you commit the current transaction, that is make all the changes permanent in the database, make it visible to the user and begin a new work, or you could roll back the transaction, which means that all the changes that you had done are rolled back and the transaction basically aborts. So, in almost all systems by default, every SQL statement commit implicitly, and if it is been able to execute successfully, otherwise it rolls back. and this implicit commit can be controlled also. It can be in different systems, there are different ways to control that and say that I do not want implicit commit, I would only want commit to be done explicitly. So, for that purpose, a part of SQL called the transaction control language has different instructions: a commit to save the changes, roll back to roll back the changes, undo the changes, and also to do it in some controlled way by defining save point, and you can also set a particular name to a transaction and its behavior. So, let us look at examples for doing that soon. And these TCL commands are used with specific DML commands. They are meaningful in terms of insert, update and delete only. For example, if you are creating a database or you are doing a select to data retrieval, then these instructions have no role in those transactions. So, commit is a transaction command which is used to save changes and make them permanent based on what has been invoked. So, here you see the example of a customer database, and what I am showing is if you this is the initial state of that table, and before any value has been deleted, and if you do select star from customers, these 7 records is what you get to see. In view of that, you do a delete and then you commit the delete. So, you say that I have deleted and make that deletion permanent. So, deleting based on age. So, this record is supposed to be get deleted and this record is supposed to get deleted, and after I have done the commit, then again if I do the same data retrieval, and now I get to see 5 records only, the 2 record number 2 and record number 4 have been permanently deleted. So, this is the way you can explicitly do commit and make the changes permanent. In terms of rollback, it is a command which is used to undo transactions, that is the changes that have already not been saved to the database, you can roll back. So, you can roll back or undo transactions only back up in history up to the last commit or the last rollback command was issued on this. So, again looking at the same example, this is the initial state and then you did a delete as we did last time. So, these 2 records are to be deleted, but then instead of commit we have given a rollback. So, as you give rollback, this deletion operations get undone. So, these 2 records are again back to the table, and so after the rollback if I again do the select, I will get to see the 2 records back in my list. So, this is the purpose of the rollback command. Now, you can a transactions often could be long. So, within the transaction you may want to mark certain points, so that in case you roll back or you need to roll back, you can roll back to that particular point, and those points are in the transaction are known as the save point. So, this is the format, you say save point and give it a name, and then later on you can use those save points for your purpose of rollback. So, you are again if you are doing a rollback, then you instead of just doing rollback, you now use the save point ID that you had used in naming that particular point up to which you want to roll back, and do a rollback, and that will happen only up to that point. So, let us look at an example. So, here it is a series of instructions in a DML transaction. So, I initially set SP1 as the save point, that is I may want to roll back to the beginning. Then I delete one record, say ID 1. So, one record gets deleted, then I again save another save point, another save point SP2, this was SP1, and then delete a second record, another save point, delete another record. So, now I have a control to undo. At this point I have a control to undo to 3 points. For example, if I do a rollback to SP3, I will roll back to this point, where only this record will be deletion of this record will be undone, but the first 2 records will still look show as deleted. But if I roll back to save point SP2, then 2 records ID 2 and ID 3 that were deleted, their deletion will be undone and only one deletion will lookup. Similarly, if I roll back to SP1, it will show that no deletion has at all happened. So, if I do that on the this is the initial state on the left, the initial state of the database, 3 records have been deleted, and then I do undo of the first deletion of the first 2, and so I roll back to SP2. So, then when I undo the deletion of the last 2 records, then the what I see is the records which are marked as ID 2 and ID 3, which were done after SP2 was marked, which were deleted after SP2 were marked, they are back into the table, whereas the deletion of SP1 is still in effect, and therefore, the deletion that was done after SP1, that is of record ID 1, is still missing, and in this way you can control and roll back to any specific point in a database transaction. You can, once you have marked a save point, you can also release the save point, that is you can choose to forget that save point. Once the save point has been released, you cannot roll back to that save point naturally. You can use set transaction command to initiate a database transaction also, and it is typically used to specify the characteristics of the transaction, particularly if you want to say whether a transaction is a read only transaction or a read write transaction, then you can do it in this way. You can say set transaction and give a read or write flag, read or write or read only flag for that. Let us quickly take a look at a different form of serializability besides the conflict serializability. This is called view serializability. So, in terms of view serializability, we again define what is known as when are 2 schedules defined to be view equivalent. Earlier you remember we defined 2 schedules to be conflict equivalent. Now, we are defining view equivalent. So, there are 3 conditions. The conditions are simple. What conditions say is 2 schedules are view equivalent if the transaction, the initial value that a transaction reads is same in both these schedules. For every transaction, the initial value that it reads must be the same between the 2 schedules. Similarly, the third condition says that the final write that is done, final value that it writes, every transaction writes in both the schedules must be the same writes should operate. And the second condition is a read write pair, that every transaction when it performs a read on the data item, it must read from the write corresponding write in the other schedule by the transaction which did the write. So, I always start with the same initial values for every data item in both schedules. I always read from the corresponding write in the same schedule in the 2 schedules, and I must write the final in every transaction, every data item must be written in the same way in the 2 schedules. So, this is again, and the equivalence is based purely on read write alone, as is the case of conflict equivalence also. So, given the definition of view equivalence, we can say schedule is view serializable if it is view equivalent to a serial schedule. Earlier we said that a schedule is conflict serializable if it is conflict equivalent to a serial schedule. Now, we are defining the view serializability. With a little bit of thought, you can convince yourself that every conflict serializable schedule is also view serializable, but the reverse is not true. So, here is a schedule which is view serializable, but is not conflict serializable. You know this is not conflict serializable, because certainly you cannot make it into a serial schedule, make it equivalent to a serial schedule, because you cannot move this write queue above the write queue of T28 or of T29. You cannot move this either. So, given that, but if you look in terms of the view equivalence, then you will say that this is equivalent to a serial schedule. And what should be the serial schedule? Obviously, there are 6 choices, because there are 3 schedules. So, there are 6 possible permutations which give you 6 different serial schedules, and if in that, so first condition says that I must read from the same value. So, obviously, T27 reads the initial value of q. So, T27 has to be the first transaction. The third condition says that I must do the same write. T29 does the final write here. So, in the serial schedule also T29 must be the last one. So, T28 has to be the middle one. So, the serial schedule that this is equivalent to is T27, T28, T29, and the one reads and the other two writes, and T29 performs a final write. So, you can see that this is not a conflict serializable, but this is view serializable. And if you note the view serializability, moment you have view serializability and you may not have conflict serializability, then you must be having certain blind writes. These are called blind writes. These are blind write in the sense that here you are writing the value of q in T28 without having read its current or previous value. So, you have just blindly, you have just computed some value and you are writing to that. So, if a schedule is not conflict serializable, but is view serializable, it must have performed some blind writes where it has written data without actually reading it. So, this is a weaker form of serializability that is possible. Now, the question is similar to conflict serializability, where we saw that a schedule can be conflict serializable if its corresponding precedence graph is acyclic. So, we would like to find out similar test for view serializability, but as it turns out that trying to find out this is exponential in cost in terms of the size of the precedence graph. So, it has been proved that the problem of checking whether a schedule is view serializable is in the class of NP complete problem. So, if you are good in algorithms, you will know what NP problems are and when are problems called NP complete. In very simple terms, even if you are not familiar with that depth of algorithms, you can simply note that if an algorithm is NP complete, then it is extremely unlikely that there exists an efficient algorithm for it. There exists any kind of polynomial time algorithm. It is extremely unlikely, it is still an open problem in computer science whether at all polynomial algorithm exists for NP complete problems, but it is extremely unlikely that an efficient algorithm will exist. You may have some approximate algorithms which can give sufficiency conditions, which can say that, well, if these conditions are satisfied, then necessarily a schedule is view serializable, but not a sufficient condition, not a necessary condition. That is, in other words, that there may be some schedules which do not satisfy the sufficient condition, but are still view serializable. So, using view serializability have certain problems. So, here I have worked out a longer problem in terms of the view serializability to check that. So, it is kind of a brute force algorithm. So, if you see, this is the schedule given, there are two data items A and B, and there are 3 transactions T1, T2, T3. Since there are 3 transactions, then if I want to prove if it is view serializable, then what I will have to do? I will have to find one of the possible serial schedules which is view equivalent to this. So, first I list out all the serial schedules. Given 3 transactions, there are 6 serial schedules, and then I first start with condition 3, which is who is doing the last update. So, there are writes are only on B. So, and last of that are being done in all the 3 transactions. So, there is no write on A. So, the list of final update on A is empty, and for B the order is T1, T2, T3. So, T3 does the last. So, it must whatever schedule this whatever serial schedule this given schedule S has to be view equivalent to must have T3 as the last transaction to execute. So, only these 2 are the candidates which may be view equivalent to this schedule S. So, we reduce down, and now we have only to decide whether these 2, any of these 2 are view equivalent to the given schedule S. So, moving on with that, now next we check condition 1 and condition 2 together. So, condition 1 checks that they must read the same value in both the schedules. So, we see that these are the reads that are happening on A. So, we see that on A there are reads happening, I am sorry, these are the 3 that is reading A. So, it happens in the order of T2, T1 and T3. So, this is what we find, and in terms of B we find that transaction 2 reads B and writes it. So, it has to be in that order. So, it reads it does an initial read in terms of T2, and then the first write of that read value is happening in the transaction T1 after the update of the read. So, that means that whatever schedule we look for in terms of view equivalence, they must have in that schedule T1 must follow T2. So, T2 must happen first, because it needs to read the initial value, and then that initial value is used by then there is a write on by T1. So, T2 has to come before T1. So, that means we are already in terms of only 2, we have seen that there are 2 possible candidates based on condition 3, it is T1, T3. So, in these 2 we only can have this one, which is satisfying the other conditions, and there is no read write sequence. So, we conclude that indeed T2, T1, T3 satisfy all the 3 conditions of initial read, write after read and the final write conditions, and therefore, this given schedule S is actually view equivalent to a serial schedule, and it is a view serial schedule and can be used safely for the transaction. There is another example given here, where there are 4 transactions R1, R2, R3 and R4, and there are 2 data items A and B, and you have to find out establish whether this is view serializable or not. I am not working out this one, this is worked out in the presentation slide, but I will not show it here. You should first try it out, and then once you have been able to do it or you are unable to do that, then you check the solution from the presentation slide. There are different other complex notions of serializability also. For example, if you look at this particular schedule, this actually is a serializable schedule. This is the effect that it produces will be same as the serial schedule of T1, T5, but if you go through the definitions of conflict equivalence and view equivalence, you will be able to show that this schedule is neither conflict serializable nor view serializable, but yet given the particular. So, if you just look at the read write, this is not a serializable schedule in terms of conflict or view equivalence, but given the fact that it actually performs simple add subtract operations on these variables, using the properties of add subtract operations, you would be able to you can actually see that this particular schedule actually is a serializable schedule, and you will get whatever initial values you start with, the value that you will achieve through this schedule and the value that you will achieve with the serial schedule T1, T5 are indeed same in every case, but this determining this requires the understanding of other instructions, other operations besides the read and write. So, this is just to show you that using the read write model and conflict and view equivalence are not the only ways of getting to serializability. There are more complex models, but we will not go into the depth of these complex serializability aspect. So, we have shown that with we have shown here that with proper planning, a database can be recovered back to a consistent state from an inconsistent state in case of system failure, and such a recovery can be through cascaded or cascadeless rollback, and we have also introduced a simpler model of serializability in terms of the view serializability, but testing for view serializability is empty complete. So, as an effective algorithm, it is not that powerful.